or okay, it works. So I will say first about a very simple way of very simple kind of localization, which is called aura localization. It is a subject which is very popular in somewhat old-fashioned non-commutative geometry. So let me see. Aura localization of rings and modules. So this is kind of algebraic rings and modules. Just to have one example in which we understand localization a little better than in other situations, and which is somewhat beyond the situation in usual commutative algebraic geometry, but the situation in the usual algebraic geometry with Zariski open sets is very similar to the situation with localization. So suppose R is a ring with unit, a ring with unit, and S in R is a multiplicative set. That means that 1 is in S, and for every S1 and S2 in S, the product S1 times S2 is also in S. Then I would like to do the following thing. I would like to consider formal expressions of the form S2 minus 1R, and I want to multiply them. So I have S2 minus 1R, and I have some other, say, S prime to minus 1R prime. And I would like that this is again of the same form. Better to say, I would like to embed ring R if it's possible, or if not embed, at least to have a map into a ring which I would call S2 minus 1R, which contains R as elements in R will be of the form 1 to minus 1 times R. Oh, sorry. So if R is element in a ring, 1 to minus 1 R will be kind of its copy. But I would have a more general copies, such that if S is indeed invertible element already in R, then this would be the usual inverse. And so where S prime will be in S, and R prime will be in R. So I will simply consider this as formal expressions. Consider set S times R, and I would like to make it a ring. This is just my wish. It's not. This is not yet a recipe. It's not yet well defined. Nothing. But I would like to see what kind of obstacles come. And R is not necessarily commutative. In general, it's non-commutative ring. In commutative situation, you know this appears. You have categories. You have rings of fractions of commutative rings where you take some multiplicative set and you simply invert these elements in the ring formally. And this is related to the story which I had yesterday, that if I have not yesterday but last time, when if we have some space and we have some observables or functions on this space, then if you take the space where f is equal to 0 away, all the 0 locus, then away from that f to minus 1 is defined. So that means that you by introducing f to minus 1, you pass to the part of a space which is away from a zero locus of f. That means from singularities of f to minus 1. So you simply, if you are on this restriction, you can consider f to minus 1 as element of a ring, which is, we say, localized to this set away from singularities of f to minus 1. So let's see what's the problem here. So I would like that this is again of the form s to minus 1r for some s. So for this to be able to do, that would be easy if it would be commutative. Then I would take, you see, s times s prime, s minus 1 to s. This is s prime, s all to minus 1 in a ring. This would be a kind of good recipe to take if these guys would be one next to another, but they are not one next to another. So what would you like? You would like to interchange these two things, that s comes here and r comes here. And so I have s to minus 1. And then, however, we cannot maybe choose the same r and the same s. But we can choose maybe some s tilde to minus 1 and some r tilde, r prime. And then do the trick which I said before. So s tilde s all to minus 1 times r tilde r prime. Now let's see what I wanted to have. So I wanted to have that I replace this one with this one. And the tilde guys are new guys. So for every r, for every s prime, I want to have s tilde, and I want to have r tilde, so that this is possible. So if I multiply this by s tilde from the left, and by s prime to the right, then if this is still a ring, I want that this guy is a ring. Then I would have s tilde r equals r tilde s prime. So this condition would be if I have s tilde and s, if all these guys in s's, if they are invertible, then I need this condition for every r, this is in r, for every s in s, there exists s tilde in s and r tilde in r, so that I can do this. So this didn't need to be called s prime. It could be any maybe it's better than this is r and this is s, but I really wanted to motivate that this is one fraction, this is another fraction. So so this seems to be necessary, but it's actually sufficient. So I want to have to embed r into some ring s to minus 1 r. So we can do in general. Want a homomorphism, which is a minimal in some way, such that all elements in S go to invertible elements, invertible in S to minus 1 R. And I want to do it in a universal way. So in a universal way, so if there is some other ring, say R prime, also a ring, and S consists of invertibles, then I want to have a unique, then I want that this map factorizes through S to minus 1R. And it appears that if S is ORE, and that means this condition, plus one more condition if R is not a domain, So that means, again, for every S in S, for every R in R, there exists S tilde, there exists R tilde. I'm not writing R prime anymore, such that SR is RS, but tildes are on the left. So better to say left or in the case of R is domain. So if R is domain, R is domain. If it's not domain, then there is one more condition, but this condition is more instructive for this course. So there is also so-called left cancellability. Also, some new guys appear on the left, and there is some cancellation property. But say I take that R is domain. People in commutative ring theory usually call by domain, and they call it integral domain if there are no zero divisors, and if it's commutative. But people in non-commutative ring theory, they also call it integral domain or only domain, and they don't require that it's commutative ring. So in these conditions, I can define by the above recipe, this recipe multiplication on these fractions, and appear that these fractions really give, with the map I said R goes to 1 to minus 1R. In this concrete realization, of course, I'm looking if there is a universal object, and universal object is there if S is ORE, and in that case, this map is this map. R goes to 1 to minus 1R. So we, in universal, in the minimal way, we inverted elements in a set which is ORE set. There are ways to invert sets which are not ORE. There is a more general localization which is called Gabriel localization, which can invert in more general sense, and this is a special case of Gabriel localization. Well, now if you have a module, module, so I will all the time work with left modules. Is a left module over R. Then you can define also S to minus 1M. Well, you can define again, well, I didn't say something. I didn't say something important. Of course, some fractions will be the same. This is not S to minus 1 R is not S times R. Just pairs, formal pairs S to minus 1 R, but there is also a relation of equivalence. And similarly here you will have that this will be M cross R divided by a relation of equivalence. And this relation of equivalence is easy to guess. No, when we ask our first year students how to define rational numbers, then we ask when two fractions are the same. So the same story is here. So we want that S to minus 1R is equivalent to, say, S prime to minus 1 R prime. So what would you like? You would like to put two fractions to the same denominator. This is the most important thing. Without putting them to the same denominator, you cannot compare them, and you cannot add them, because I defined only how to multiply them, but I also need how to add them. And similarly, the situation will be here for modules. So let's see. So I would like that. So if I have, say, remember usual fractions, say 4 over 6 and 6 over 9. Well, we had the recipe that's 4 times 9 is 6 times 6. but we could also put well, we could in the case of rational numbers, we could also take one fraction with the same where the two parts of the fraction are mutually co-prime, but I could also put common denominator 18, or I could and then I could compare them also when I add them, common denominators. So let's see. So I would like that this s2 minus 1, I would like to multiply this s with something else, say with some r, and s prime, say with some s, some new guy. I certainly can do this because s is in s prime is also in s, but it is in special case in r. So if s is in s and s prime is in r, then I can find the new guy on the left, so that this is the same. And because this set S is multiplicative, this here, the whole thing is in S. So the whole thing can be inverted. And this is a multiple of S, and in the same time, multiple of S prime. Exactly the situation which we usually do with, so let's see. If I have here s2 minus 1r, I will put, instead of s, I will put s times r tilde 2 minus 1 times r tilde r. You see, this would be s2 minus 1 r tilde to minus 1 if this would be inverted, times r tilde times r. R tilde to minus 1 is not invertible. However, this is consistent if I just say that this is equivalent to this. I can put this condition, and this is a special case of this condition. So I call these two guys equivalent if there exists r tilde and exists s tilde, such that this kind of fraction, so that this is the first condition, and the second condition is, well, I need, I extended this guy, so I do the same, and I can compare them now. So here I will have also SR tilde, so I will have RR tilde. You see, this is how I extended. RR tilde equals, and here I will have R prime S tilde. So this kind of extensions you can do by Ore condition, but this together is a condition on two fractions, that these two fractions are the same. So if, so both are satisfying at the same time. And then this here is the same as this. This here is the same as, well, S tilde S 2 minus 1, S tilde S. And then the denominators are the same. So the two guys are the same if R tilde R is the same as wait a second. As I have written wrong. R prime. So I extended. Sorry. I simply S to minus 1 R, I want to be the same as this one. This I want to be the same as this one. I just extended one and this by S tilde. So for this one, it's trivial because I can do S to minus 1, S tilde to minus 1, S tilde R prime. Of course, this is just plausible ansatz. I have to really check that if I define it this way, that everything is consistent. I'm defining this ring. I'm not, if there would be such a ring, then this would be true, but so that this is the same. So this is the same if this is the same as this, and this is natural to expect, that I can multiply the denominator and the numerator by the same ring element from the same side and get the same. Then these two conditions together mean that basically this is the same. That means that this should be the same. So this is the relational equivalence. And then you see that now with this first condition is always possible. So if these guys would not have the same, this second condition, so then they will be comparable. I could bring any S and S prime. I could always choose R tilde and S tilde and put them to the same denominator. And then I can add them, because I can add R and R prime. I can add if they have the same denominators, and this is the recipe. The first half is telling me the recipe, so I can add these things. And now you have to prove that this addition is well defined on these classes. So there is a work, you know. It takes several hours to prove all the properties that you really get a ring and etc. It's not a two-minute job, but it's straightforward. It's an exercise. When I learned it first time, I just saw the statement. If it is or, and you take this multiplication, then you get a ring and universal object. So it is an exercise, and it's very useful exercise. It will take you a while to prove it, but you get it. And now for modules, you do the similar situation. You also take M cross R divided by similar relational equivalence. But instead, you can do the following. You take S to minus 1M and define as S to minus 1R. And you tensor it over R with them. You take the tensor product over the ground ring, because S to minus 1R, M, so M is a left R module. And now S to minus 1M, you can multiply from the left with S to minus 1R, because the first tensor factor is a ring, and you can multiply by S to minus 1R. So S to minus 1M is now S to minus 1R module. So and this easily, if I have map from M to N, then you also have induced map from S to minus 1M to S to minus 1N. And you get a functor. So let's see, new page. You get a functor from left R modules to left S to minus 1 R modules. And I will call it Q upper star S. Q stands for quotient. No, there is a construction of quotient ring, or here rings of quotients. You see these fractions or kind of quotients, and the whole construction is in some sense quotient. But this, so QS star is basically the same as S to minus 1 R, which is considered as S to minus 1 R bimodule. And you tensor it over R with whatever is the module. And this is, of course, tensor product is a bifunctor. So it is a functor in the second argument. So this is a functor. And this functor has also a right adjoint, Q S lower star. Namely, you forget, you simply, this here is whenever you have a tensor product if you have R to R prime, not necessarily here R prime is the same as S to minus 1R. But in general, you can take any R prime and you can take any F. Then of course, you have tensoring with R prime over. And it has a right adjoint, and its right adjoint is a restriction of scalars. That means that you simply, so if you have, so a restriction of scalars goes, so call it F lower star in this case, for general R prime. Here we will call it QS lower star, from modules to R modules. Then you multiply R times M, M is in M, simply by taking F of R and you multiply by M, because M is a module over R prime, but here I considered M as R prime module, as R. At the beginning I had R prime module, so you multiply by F of R here, and that is the definition of R times M here. So this is the restriction of scalars. This has further right adjoint. So we have F upper star, you have F lower star, and then we have F upper shriek, which is certain home. It's not important today to go into these details, but in general, whenever you have a map of ring, you have a joint triple of functors. A joint triple, and F lower star is faithful. Functor. Is faithful. So the situation is here is the same, but I can consider situations which are more general, in which I don't have the third guy, and I still have similar situation like here. But you see, in this situation, so I have Q low S lower star, and this Q lower star will be embedding of categories. So QS lower star is embedding of categories in this case, not in general. Well, for this affine adjoint triples, this is faithful, but here is fully faithful, because you see, if I look at the this localized module, so this thing, this is called the localization functor. In this case, is Ore localization functor. In this case, is Ore localization functor. But if you have already something what is localized, that's so if I would take S to minus 1 R tensor with over R with S to minus 1 R over M, that is the same as S to minus 1 R over M. Because this means, you see, you remember we had those, here are fractions. This is basically S to minus 1, oh, sorry, copy of S plus M, and then by some relation of equivalence. Now you inverted elements in S from the left. Now, if you again invert elements in S from the left, then these S's will join these S's. It can easily be proved that this is the same. That means that that if I go here and then back, then this functor Q S upper star will not do anything to the images of guys here. So basically, that means that S to minus 1 R modules I can observe in the former category in R modules as a subcategory. So this is the subcategory, or which is essential image of this functor. That means S to minus 1 R modules. So that means that S to minus 1 R modules form the subcategory of R modules. That's quite amazing. So, so you have your original category R modules. Inside, you have those guys for which Q upper star doesn't do anything. These are the guys where those modules where every element in M you can multiply by inverses of S in consistent way. And so you have this and you have this. So you have Q upper star, you have Q lower star. Now I will not write S anymore because it's in general situation. So first Q upper star, this is left, this is right. That means that I have a unit and co-unit, as I explained last time, from identity. Where is identity? We'll see in a moment. Q upper star is on R modules. And this is on S to minus 1 R modules. So this is identity on R modules. On R modules. And here is to identity on S to minus 1 R modules. And they satisfy the triangle conditions. That means that you have a junction. And in addition, Q upper star is embedding of categories. That means that it is full and faithful functor. Full and faithful functor. And this, so this situation that you have pair of adjoint functors, and then this Q lower star is fully faithful, is equivalent to that epsilon is iso. So epsilon is isomorphism. This is a natural transformation. So that means that every component of epsilon for every module M is an isomorphism. So let's see this situation a little bit more. So we want to consider Q upper star, Q lower star on on n. Now n is, and I want to have a map to n. So n is already localized module, S2 minus 1R module. It's object of S2 minus 1R modules. That means that I already can multiply with guys of the form S2 minus 1R. And now I forget that I can do this. And now I localize. So that means you again multiply with S2 minus 1R. So you have something like S2 minus 1, S2 minus 1R. And this doesn't do anything because I already, well, maybe it's better to write, I have n, which is, I already have S2 minus 1s here. And then when I multiply with this, I don't do anything because S2 minus 1 already is here. So I can simply, all S's, if I have S cross n, every S I can move here. So I can write it, this pair, I can find the equivalent of the form 1 for 1n. So if I have Sn, I can write it as 1n prime. So that simply n prime is simply Sn. I put here S to this side. I mean S2 minus 1n. So n prime is simply S2 minus 1n. I can multiply with S2 minus 1. So basically, this guy like doesn't exist. But this is far more general situation. So that's the situation. So if I would have this Sn class of this goes to 1 S2 minus 1, and that's this is a map. So I've forgotten that n is there, but now it's just like a module over R. I do for the module, I do the usual construction. And then I say, well, every of this guy is actually an n. I take just this class, and such guys correspond to just S2 minus 1n. So this composition is exactly this map, and this map is isomorphism. That I said, not only that it's defined, I don't lose any information in that can be checked, and this is the isomorphism. This isomorphism epsilon n. So this is true in general. In general, we take any categories C and D, and I have two functors, Q upper star and Q lower star. So Q lower star is epsilon is iso. So the co-unit of the junction is iso if and only if Q lower star is fully faithful. And you see, now you have 2 points of view. One point of view is, in the case of order localization, I'm inverting some elements in the ring. Another point of view is, I'm considering its category of modules and considering the localization functor. And for this localization functor, I am making a functor which ends in something what is essentially a subcategory. This D, if it's fully faithful, that means that D embeds in C. I don't lose any information. It's a faithful functor and it's a full functor. So D is D is essentially a subcategory of C. And this is pair of joint functors. So such situation we also call a localization. Of course, this is so. Of course, Q upper star is left adjoint to Q lower star. Epsilon is ISO, and Q that is the same as Q lower star. And sometimes we call these localizations. Moreover, there is one more sense in which you can consider that this is localization. Namely, you can consider in the category of R modules, inside this category, you can consider morphisms. So I have F goes from M to N is a module. Now you consider S2 minus 1 M to S2 minus 1 N. This is the localized model, so better to say Q upper star M to Q upper star N. These are the localized modules. And you have this Q upper star F. This is a functor, so there is induced map. If these are pairs, just if this is like S cross M to S cross N, on M to N is just doing F, and on S part is like identity. And so Q upper star is a functor. And now it's possible that some guys will be here, that some of these maps will be invertible, which were not invertible before. So similarly, like in a ring, I inverted some elements. In R module, I invert some morphisms. So basically, you see, you can say that this localization from R modules to category D is just take it abstract. Just take it abstract. We mean S2 minus 1 R modules, but take it abstract, and you realize it that way that you look at all F's such that Q upper star F will be invertible morphism in that category. So if Q upper star F invertible, then you just formally invert that arrow. So just add some arrows here. So D, objects of D is the same as objects of R modules. However, invert formally those F such that Q upper star F is invertible. And then you get again localization. So in general, I can have any category C, I can have any category D, and I consider here some sigma, some set of arrows which will become invertible in D. So these are arrows invertible in D. D is in this case not a subcategory, not a localization, anything. Then if you take these arrows invertible in D, then up to set theoretic problems, theoretic questions, according to Peter Pierre Gabriel and Sisman. This is very much used in homotopy theory. They wrote a book where they applied this to homotopy theory in late 1960s. And this is homotopy is about inverting certain arrows, and then they define category sigma to minus 1 C, a universal one, such that all those in sigma will be invertible. But here you take exactly those which become invertible arrows, which become invertible. That means if S is an arrow, I call it S like an element in the ring before which I inverted, but now it's a morphism. And then I want that f of S, this functor of S, is invertible. Invertible in the sense isomorphism in category D. And you take all of them and you invert them. And there is a formal construction how to do that. However, in that case, you do not have only S2 minus 1 here. Objects are the same. So objects in C are the same as objects in C. So this is the new guy. This you define as the same objects. But then arrows are zigzag maps. So you allow not only Fs, but you can invert, you can take another G and then another invert and so on. So you have a kind of finite sequences of arrows in C and formal inverses of arrows in sigma. And such guys compose. This is a well-defined category, and there is a natural map from this to this. Namely, objects go to the same objects. Objects are the same. And morphisms just go to, not to the chains, but F goes simply to F. And so this construction you can look up in Gabriel and Sisman book. And this is a general localization. We call it Gabriel. When somebody says Gabriel Zisman localization, sometimes they mean this, and sometimes they mean that it has analogs of Ore conditions both from the left and right, or only left or only right. So they those cases are close to the situation where either left this Q lower star that you have this other other function in opposite direction. Here you do not need to have for this localization where you invert a general family of arrows, which you can assume that it's which you can assume that it is multiplicative. And by the way, we inverted here, so the whole thing will now factorize through a sigma to minus 1c, and that's why we do this construction. This is again universal in some sense. So in this case here, I do not need to have a right adjoint. And above, I had such a situation. This situation from below that I was inverting some morphism was true, but in addition, I had this right adjoint which was fully faithful. So the localized category is really part of the original category. This is not and this situation is very similar like in Sheaf theory. Well, it has many connections to Sheaf theory. I will explain that in one of the next lectures, not today. But one of them is that if you have a category of pre-sheaves and category of sheaves, and I have sheafification, which I explained last time, and in opposite direction, you have pre-sheaves, which are sheaves, which satisfy the sheaf condition, embed in the category of all sheaves. So, and I have pair of adjoint functors, and here I have fully faithful. So exactly the same situation, epsilon and isomorphism, you can construct it directly using germs. In that case, that's one parallel. There is another parallel, namely for oral localization, a special case of what I called Gabriel localization. By Gabriel localization, I don't need Gabriel and Zisman localization. It's not the same word, but it's the same Gabriel, who just died like maybe 3 years ago. He done quite a few things in localization theory, but one of them is working with categories of modules and considering more general localizations of categories of modules. And he had the construction of such one. He had several constructions of those, or several ways to talk about it. One of them considers so-called Gabriel filters or Gabriel topologies on a ring. So a ring can be in certain sense well, there is certain kind of topological construction, and this construction can be reinterpreted in terms of what we call additive Grothendieck topologies. So Grothendieck topology is not a topology in the sense of topological spaces, but it tells you which morphisms, as a generalization of open sets, cover some object. So you have families of morphisms which covers some object, and if you know them, you can define a notion of a sheaf, and then you have a sheafification. Now, in the case of modules, you can do additive version of this. Namely, you take the same thing like a Grothendieck topology, but with values in abelian groups. You consider the yes, in a sense, you don't consider in the category of sets the whole construction, but in the category of abelian groups. And then sometimes they call it also Gabriel topology, and do exactly sheafification in that situation, and sheafification will be Gabriel localization function. So this Q upper star is a sheafification function for something, and this is embedding of sheaves into pre-sheaves, which I last time explained in two languages. One was in the language of pre-sheaves, another was in the language of étale spaces, and the two were equivalent. So today I told you a rather long story about several kinds of localizations. At the beginning, we had oral localization as an example, where we invert some elements in a ring in a consistent way. You need it to in such a way that only one-sided fractions, not zigzags. You see here we have zigzags here. So if f would be if I would have arrow f, then s to minus 1 is going opposite direction than s. And you have g, then you have s prime to minus 1 in the opposite direction. So it's zigzags. But all these guys which go in the wrong direction belong to sigma. So this is in sigma, and this is in sigma. And such maps are new maps in the category with the same object. So this is more general. And then we have such a situation where in addition you have a right adjoint, which is fully faithful. And then all the Gabriel localization, all the sheafification functors are examples of this. Now you can see that there are a little different motivations will be in this situation for sheafification. We were sheafifying on the whole space and localizing. When we went away from singularities, localizing was more going to part of a space. So geometrically it looks differently, but it is a special case of the same abstract situation, categorically speaking. So I will finish my first lecture and then I have to record the Zoom. So I will go away to